Hi class, this week we're going to look at chapters 9 and 10 of your text. Chapter 9 specifically is about developing meanings for operations. And it focuses on helping students connect different meanings, interpretations, and relationships to the four operations of addition and subtraction, which are inverse operations, and multiplication and division, which are also inverse operations, so that they can accurately and fluently apply these operations in real-world settings, which is the ultimate goal of education, that we learn something useful and applicable. This is all part of the operations course, in which students learn to see mathematical situations in their day-to-day lives, or that they're also able to see these mathematical situations in contextual problems that you create within your classroom so that they can begin to make models of these situations. This whole chapter is about helping students develop operation sense. One way to really ignite student interest in mathematics is to use contextual problems that model real-world scenarios, or even using them within the problem. If you do so, that makes the problem relatable, and it will help to activate their problem-solving strategies. The context that you're going to put these problems in, again, are going to be something that is familiar to the students. And the important thing for you is to make sure that the students, through their problem-solving strategies, are using numbers, words, or pictures that make sense, that their problem-solving process can be expressed in a way that's logical. Within the next two slides, we're going to look at three categories of problem structures for additive situations. These three structures are called change problems, part-whole problems, and compare problems. I want to encourage you to explicitly teach your students these structures so they can identify important characteristics of the situations and determine when to add and when to subtract. With respect to change problems, there's two types: join problems and separate problems, and they're illustrated by the graphics that are on your slide with A and B. Here's an example of a join problem. Molly has 8 pennies and Mike gave her more. She now has 12. How many did Mike give her? This could be modeled by joining 8 to something unknown and being set equal to 12. How about a separate? Well, let's say Molly had 12 pennies to start with, but she gave some to Mike. She now has 8. How many did she give to Mike? So we need to separate the whole and a part and find the leftover. That would be modeled by 12 minus something unknown equals 8. So those are two types of change problems. And notice, for both of those, they deal with the same exact units. What about a part-whole? Part-whole problems are also known as put together or take away problems. They're different from change problems because there is no action of physically joining or separating the two amounts, and they don't have to necessarily be the same units. In these situations, the whole might be unknown, one of the parts or both of the parts might be unknown as well. An example would be this. Let's say Claire has 4 pennies and 8 nickels. How many coins total does she have? Or Claire has 12 coins total. Some are nickels and some are dimes. How many of each could she possibly have? And you see the graphic of the part-whole demonstrated on the bottom of your screen in the right-hand corner. The last type of structure are compare problems. Compare problems involve the comparison of two quantities. The third amount in these problems does not actually exist, but it's the difference between the two amounts. Like part-whole problems, compare problems typically do not involve a physical action. Comparison problems generally use the words how many more or how many fewer. For instance, the problem: John has 4 fewer pennies than Sam. Sam has 12 pennies. How many pennies does John have? That represents a compare problem. I do want to make a note of something that deals with mathematical terminology at this point, and it's the difference between semantic and computational equations. A semantic equation has an unidentified part plus a known part equal to a whole. A computational problem has the two known parts on one side equaling the unknown. And in math, we've often been taught to always put an equation into computational form because we're looking to find what the answer is equal to. But it's really important that you start to show your students from early on that both forms are equivalent, because the somatic form is the one that usually students will initially write a problem out in because it mirrors the order of the words. So again, if you can take opportunities to show them, like the problem on the screen, that blank plus 5 equals 11 really mirrors the same exact concept as 11 minus 5 equals blank. Okay, I'd like you to take some time and read through A, B, C, and D on the slide here, and then try to identify the structure that each problem represents. To check your understanding, you could look in the notes section of the slide. I identify which each structure is. This screen presents a contextual problem and a student's explanation of how he solved it. You'll notice in the problem that real students' names were used, and that's so helpful within your classroom to make the problem relevant and relatable to the students by using their names. It ignites their interest and really gets active learning happening in the classroom. Some different ways you can derive some contextual problems is by using recent experiences in your classroom, whether that be through field trips, children's literature, art, science discussions. All of those are fruitful ways that could yield great contextual problems. A couple of things I do want to mention before moving on. One thing that really differentiates contextual problems from solving story problems is that not only are they relevant to the students in your classroom, but you really want to emphasize the need for students to explain or put into context what they did within the scenario that you've presented. And it needs to be done so well enough so that someone else can understand it. This is a huge vital part to developing mathematical literacy and computational fluency on behalf of your students. Having students share and perhaps grade each other's work is one way to achieve this end. It's important too that when we are designing contextual problems that you choose numbers that are appropriate to the Common Core state standards. So for instance, you'll want to use numbers between 0 and 10 for kindergarten, up to 20 for first graders, and so on. So check your state standards to make sure you're using appropriate numbers. In addition, you want to begin introducing the minus and plus signs in kindergarten and continuing to do so in first grade as a way to record thinking. The equal sign should also be introduced, and you want to make sure that you define it as meaning is the same as. I think sometimes students associate equal with meaning the answer, but they're going to often be using equal signs just to show that one expression is totally equal or equivalent is the same as a whole nother expression. So if we can start out by just phrasing it as is the same as, that will help students make that connection early on. Let's continue talking about teaching addition and subtraction. Many of your students will want to use counters, bar diagrams, or number lines to solve story or contextual problems. The figure on this slide to the right shows some different part-whole models for 5 plus 3 equals 8 and 8 minus 3 equals 5. Notice that in every example, both of the parts are distinct, even after the parts are combined. Let's talk about the number line, which is pictured in the lower right corner. A number line is an essential model, but it actually can initially present some conceptual difficulty for students below second grade. This is probably partially due to the students' difficulty in seeing the unit. And this could be a challenge because it appears on a continuous line. But it's very important that students become familiar with number lines early on, because they really begin to use them heavily in third grade when introduced to fractions. And it's important when you are introducing students to the number line that you really focus on the space between the tick marks. That space or length is the unit. And if students just look at the tick marks, they can totally miscount or misjudge the number line, but you want them to be thinking of the number line as measuring a length unit, and each length unit is equal to 1 unit. Using arrows or hops like you see in the lower right hand corner of the number line can help to illustrate the length concept as we see with 5 plus 3 equals 8. If you would right now, go ahead and take some time and read activities 9.2 and 9.3 on page 176 of either your book or your e-text. In fact, just hit pause right now, maybe go grab a cup of coffee, and come on back after you've had a chance to look at them. Alright, now that you've read the activities, let's talk about something. Note that in both activities you end up with two distinct parts even when there is a removal action. The removed part remains on the mat, for instance, as a model for an addition equation to be written after writing the subtraction equation that you use to solve the problem. A discussion of how two equations can be written for the same situation is an important opportunity to connect the operations of addition and subtraction. And it's a way to connect the semantic with the computational form of equations. And it's really important for students to learn early on that they need to think about subtraction as another form of addition rather than just take away. So they always want to be thinking of subtraction in the form of addition because it helps them to master their subtraction facts. Because the tiles for the remaining part or unknown addend are left hidden as they are in B on your slide, you see you have that little yellow hidden part and you have the so many shown blue, I think it's 4, yes, you have your 4 blue cubes shown. A child doing this activity is encouraged to think, okay, what goes with the part I see to make the full total 9 tiles? And so they start to think of subtraction in the form of addition. We can't finish our discussion of addition subtraction without talking about some properties. Specifically, we're going to talk about the commutative and the associative property. I think probably for you as young adults, the commutative property seems blatant, but it's not necessarily so for children. Well, you should definitely use the precise title of the properties when you introduce them to students. Know that what you really care about is a student's understanding of the property itself. For instance, one way to really help students understand and perhaps illustrate for you the meaning of the commutative property is to make 2 sets of counters and then just reverse the order of them. That's one way to illustrate it. Talking about when the property works with recognizable numbers and perhaps really large ones is another way to help make the properties even more understandable for students. So saying, okay, we know that 3 plus 10 is equal to 10 plus 3, but how about if the numbers get really large? Is 100 plus 130 equal to 130 plus 100? If you get dialogue going, you'll have an opportunity to illustrate to students that the property holds regardless of the size of the numbers. And so that's a really fruitful and deeper understanding of the property. The associative property is critical because it helps students to add efficiently by looking for addends that produce 10. And you see an illustration of that with the graphic at the bottom right on your slide. And in addition, activity 9.4 on page 178 of your e-text is an excellent activity for helping your students become fluent with the associative property and with honing their instinct to produce units of 10 or anchors of 10, because it helps them to add much more quickly and correctly when they do so. Another thing I wanted to stress, while we want to focus on student understanding of the properties, you do always want to use the actual names and don't give them nicknames or don't shorten them. I made the mistake during student teaching so many years ago of shortening the associative property to the first 3 letters and writing it all over the pre-calculus chalkboard in the classroom I was student teaching in. I will never ever live that one down. So, note to self, just write the properties totally out and it will help it to sink in for students, and it will help them not to giggle like crazy in your pre-calculus classroom. Okay, we're going to move on to multiplication and division problems. Most researchers identify 4 different classes of multiplicative structures: equal groups, comparison, area, and combinations. The first 2 are most prevalent in elementary schools, equal groups and comparison, and the latter 2, area and combinations, are used in 3rd grade and beyond. It is important to know that these structures are used not only for multiplication but also for division because they're inverse operations. Within the equal group problem, which is usually the first way that multiplication is introduced, you have one number, which we call factor, and it usually stands for, represents how many groups are involved. The second number or factor tells the size of each of these groups, and the third one, which is your product, tells the total within all of the groups. I want to show you a couple examples of problems that fit within the equal group structure. Let's say you pose this problem to your students. If apples cost 10 cents each, how much did Jill pay for 5 apples? You have one type of item that's costing an equal amount. You could also pose an equal group problem through division. Let's say you said Jill bought apples at 10 cents each. She spent 50 cents total. How many apples did she buy? So this is a way for students to quickly recognize this is an equal group problem. This is multiplication. I'm either going to multiply or divide depending on the structure of the problem to find the solution. Another type of common multiplicative structure is the comparison problem. And it's not so much important that students are able to name what type of multiplication structure a problem represents, but rather they realize that it's a multiplication problem, period. And so the more examples that you can provide your students, the more they're going to be able to hone in on, okay, I'm going to use multiplication or division to solve this problem. With comparison problems, you're not necessarily looking at equal groups in a blatant way. Instead, the problem presents 2 groups whose size are being compared, for instance, and one is a multiple of the other. So the phrasing is different. And within these problems, there are 3 possibilities for the unknown. One could be the product. And here's an example of how an unknown product would be phrased. Let's say you were told Jill picked 5 apples. Mark picked 3 times as many as her. How many did Mark pick? 3 times 5 would be 15, so that's an unknown product. It could be the actual group size, and here would be an instance of a problem with an unknown group size. Mark picked 15 apples. He picked 3 times as many as Jill. How many did Jill pick? So we realize that we're using division here, and again, it's a comparison between 2 quantities, so we'd have 15 divided by 3 is 5. Lastly, it could be number of groups that is unknown, and here would be a problem that is phrased with an unknown number of groups. Mark picked 15 apples. Jill only picked 5. How many times as many apples did Mark pick? And students would know division is the key, and they would do 15 divided by 5 to receive an answer of 3. The last 2 multiplicative structures are area and array problems. Area problems are totally different than the prior 2 because the product has different units than the 2 factors. So if you had a little garden plot that measured 4 feet by 7 feet, equaling 28 square feet total, you realize that your total units, square feet, are different than the singular feet that you had for length and width. An array is actually a visual representation of the equal group situation that we talked about first. So why isn't it placed with equal groups? Well, visually, it's a great lead-in to area, so the Common Core State Standards groups it with your area problems. It's so important that when you're teaching multiplication and division that you use interesting contextual problems instead of more sterile story problems. Again, if you can use something that connects students to an experience they've had in the classroom, it will really help to make the problem accessible for all of them, and it'll give them a meaningful connection to the problem. Not only do you want to do that, but you really want to focus on sense making within your classroom. So don't worry about presenting them with a ton of problems, but rather a few problems that you go over in detail and that you involve the students actively dialoguing to solve that problem. It's going to be important that you are routinely and regularly introducing symbolism with your multiplication, division symbols, and the multiple ways to write division to encourage your students as they record their thinking, because they need to realize that all of the symbols or all of the different ways to write division, for instance, mean the same exact thing. Remainders are often an issue, and within contextual problems, you're presented with so many great and fruitful ways to know what to specifically do with them, because in real life, so many division problems do not come out with perfect whole numbers, but rather with a remainder, and you need to know if you need to do one of so many things. Discard the remainder, round up to the next whole number, or round down to the nearest whole number. And let's look at a couple instances. When would you discard? Well, let's say you had a problem like this. The rope is 25 feet long. How many 7-foot jump ropes can you make from it? Well, the answer would be 3, because you could only make 3 full 7 feet long ones out of that full 25-foot jump rope. So that would be an instance where you would want to discard it. What about an instance where you would force the answer up to the next highest whole number? Well, let's say that you are told that a ferry can hold 8 cars. How many trips will it have to make to carry 25 cars across the river? Well, you would want to take 25 and divide it by 8, and you realize that, sure, it only goes in 3 times fully, but what about those extra cars that are going to be left behind? You would have to take 4 full trips in order to accommodate all the cars, so that's when you would round up. How about when you would round down? Let's say you have 6 children who are sharing a bag of 50 pieces of bubble gum. About how many pieces will each child get? Well, 50 divided by 6 is going to go into, when you divide 50 by 6, you receive 8 pieces per child. You would have 2 left over and you would just discard those. So those are some contextual instances where you would make different decisions about the remainders. It's really important that students don't just equate a remainder as a leftover, because you'll remember when you learn division that a remainder is a fractional amount of the whole. So if you were asked to divide 11 by 4, that would give you, if you were writing it in remainder form, 2 with a remainder of 3. But that doesn't mean you have 3 left over, because we know that means 2 3/4. It means you have 2 full groups and 3/4 of a group. So it's a fraction of the whole. And as early on as you can make that connection with students, the better off they will be in having a more full and true idea of what division means. Take a moment and pause this PowerPoint presentation and complete activity 9.5 on page 184 of your e-text. I think this is a nice, easy example of an active learning activity, a contextualized active learning activity, where students can become very familiar with factors and also with composite and prime numbers. Remember, composite have more than factors of 1 in itself. That would define a prime number. And it gives you an opportunity to look at all the different factors and all the different types of arrays that you can form with a given number. Another great thing for you to try would be the Factorized Applet and the NCTM Illuminations website. Remember, that link is immediately accessible within your Blackboard shell. It's really important, as we discussed with addition and subtraction, that you model the key properties of multiplication. With multiplication, it is indeed commutative. Division is not. Order does matter with division. It does not with multiplication. And one way you can visually represent that to students is with an array, as I've shown with Exhibit A on your slide. The associative property for multiplication, you could really illustrate this with a contextualized problem. Let's say you tell your students that you are going to sign them each up for tennis camp. They're going to get, as part of their registration, 6 cans of tennis balls. Each can contains 3 balls, and each ball is $2 a piece. Please figure out the total cost of balls that they will have to pay. Well, you could illustrate to them that they could do the multiplication in any order. They could do the $2 times the 3 balls per can of tennis balls and get that they're paying $6 per can, and then multiply that by the 6 cans to get $36. Or they can use another order. They could say, okay, I have 3 balls in 6 total cans, so I'll multiply those together first. I have 18 total balls, and I know that they cost $2 each. In either case, they're going to see that they indeed get the same product of 36. But you can illustrate it visually in a much more effective way, I think, than just putting out a strand of numbers and showing that you're lifting up parentheses and moving them. The contextualized problem will help it to be more meaningful and help it to cement more in their minds. A couple other key properties that you're going to need to discuss with your students are the zero and identity properties of multiplication and division. You don't just want to state the properties, but you want to present them through contextual problems because it helps the students to better reason with 0 and 1. Here's a couple examples. You could ask the students how many grams of fat are in 7 servings of celery if celery has 0 grams of fat. They then have to think that through, and they realize that 7 times 0 is 0, and that's always going to be the answer regardless of the grams of fat. Another way for them to think of it visually is, where would 0 hops of 5 put you on the number line? Well, they realize that they're not moving at all, and again, visually they're able to see the 0 property. You can also model the 0 property with an array. You could try to have them construct 6 by 0. A great property to illustrate with an array is the identity property. So showing it for maybe 6 times 1 would be an excellent way for them to visualize that property. Concerning the distributive property, for visual learners, you can use arrays just as I've shown on the screen. That might not be many students' preferred way. For instance, I just understand it algebraically, but we have to remember that we are educating students with multiple intelligences, and for many of them they are more visual, so the array does present it in another way, and it still shows you that when you decompose a problem into multiple factors, it still is equal to the overall product, and they can see that presented with the array or area that we have presented in the figure on the slide. One other thing you're going to want to talk about is division by 0. And you don't just want to tell your students, well, that's undefined and impossible, but present it in a way, again, that's put into a context. Like ask them, can you take 12 balls and place them equally into 0 groups? That helps to cement their understanding of the property because they realize they can't take something and put it into nothing. It has to have a place to go. And that's why the division by 0 is undefined. Sometimes students can feel frustrated with context problems simply because they're uncomfortable with not getting an answer right away. And there are some tactics that you're going to want to encourage them to employ so that they can generate patient problem solving within themselves. First, you want to encourage them to focus on the problem in the meaning of the answer instead of on the numbers themselves. So we want them to be thinking about process and what is actually happening in the problem. Second, you want them to focus on the structure and identify what numbers are important and which one are unimportant. You also want them to think about what the answer will tell you. If they're thinking about what the answer describes or relates to, they can then work backwards and determine which inputs or which numbers are the most important in the problem. third, you do want students to estimate their answer, because estimation is a great way to cross-check if once you get the answer it seems reasonable. And we want students to be able to think of reasonableness often by judging their actual answer with a rough estimate. I would suggest for students that seem to be struggling because a problem contains really difficult numbers, either they're very large or they're fractions or they're decimals, and the students are struggling with the computation, you can encourage them to substitute small whole numbers for all the relevant numbers in that more complicated problem. That helps them analyze context problems that seem to be tripping them up. And another thing they can do, or you can do, is once you've replaced those relevant numbers with smaller whole numbers, you can model the problem with counters. You can write an equation to solve the problem. You can then even solve it, because then the students can see that the process remains the same and they can go back and substitute their more complicated numbers in.